Hello, this is Math Jazz from Almost Cool, and we are here for Thursday's live stream. So, I have some things that I want to talk about today, mostly regarding linear systems and matrices. So, let's do that. Okay, so on Tuesday, where we left off, we were talking about systems of equations. And let's see if I can pull up. So we were talking about linear equations, and we were talking about the general form, a generalizing of linear equations to more than two dimensions. That is more than an x and a y. So here's our first example of a multi-dimensional linear function, okay, or linear relation. Okay, so what we're going to do from here is we've already talked about using substitution, and I think we already talked about using elimination to solve linear systems. And so if we have a higher order system, say like x plus 2y minus let's say z equals 0, and so let's see, let's pull that down. Okay, 2x plus y minus z equals 4, and x minus y plus 2z equals 8. So we have this system here of 3 equations and 3 unknowns. In general, if you have more unknowns than equations, then you cannot solve the system. You can find all possible solutions, but you won't find a single solution. You'll have some collection of values where they are valid for all 3 equations, but you won't be able to narrow it down to say this is the point where they all intersect. You'll say here are all of the points where they intersect. Let me draw. So if I have just a regular y equals mx plus b, if I have 2 equations and 2 unknowns, I can either get 2 lines that cross at a point, or I can get 2 lines that do not cross at any point because they're parallel lines, or I can get 2 lines that actually are just the same line in 2 different equations. For example, if I had the equations y equals x and 2y equals 2x, they look like 2 equations, but they're really the same line. And we'd see that if we canceled out the 2 in the second equation, we'd get the first equation back. So our 2 variable linear functions can either have one solution, no solutions, as in this graph, or infinitely many, as in this one. When you have more than 2 dimensions, then you have these planes that intersect each other. You can have, for example, one plane and another plane. This is where they intersect there. So this is our side view of our two planes intersecting, and from head on it looks just like an X, like this. From a diagonal view it looks something like this, where we have one plane hitting another. This would be an example where this line where they intersect here, it's an infinite collection of points that satisfy both equations, but it's not, since each plane is an equation and I have three unknowns, I have two equations and three unknowns, I don't have enough to limit down to one point. I would need to have another plane or another equation. I'm going to put this going through like this. If I had another plane, then I would get an intersection that would go like so. And I would be able to limit down to, this is the point of intersection for my three equations. And we'd call that the solution. The point of intersection. Okay, so getting back to the problem that we wrote out here, what I need to do is I'm going to use elimination several times between my three equations to be able to kill off unknowns as I go down until I get to the solution. So what I'm going to do first is I'm going to take the first two equations and I'm going to subtract one from the other to kill off the z. Notice if I took this equation and subtracted this from it, I'd get negative z minus negative z, which is the same as negative z plus z, which is 0. And then I would have one equation with two unknowns instead of two equations with three unknowns. Let's do that. So x plus 2y minus z equals 0, and 2x plus y minus z equals 4. And if I subtract this bottom equation from the top one, I get x minus 2x is negative x. 2x minus y is plus y. And z minus negative z is 0. And 0 minus 4 is negative 4. So here is my new equation. This is what I got from equations 1 minus equation 2. And I'm just writing this here as a note. You have to make sure to use all of the equations in your system as you do these combinations and substitutions and eliminations, because if you don't use all of your equations, then you lose information and you won't be able to get the solution for the system you started with. So I combined 1 and 2 and got this new equation here. And now I'm going to take 3 and I have to, well, since I got rid of the z's before, I want to get rid of the z's again. And I can do that by adding 2 times the second or 2 times the first equation to the third. Or I can just add the first and the second to the third, because negative z minus z plus 2z is 0, and that would kill the z's in the resulting equation. I think I'm going to do that, where I just add one copy of each of the first two equations to the third. So here's my third equation. X minus y plus 2z equals 8. So x plus 2x plus x is 4x. This is, of course, the equation that I got before, and I don't want to lose it, so I'll put a box around it. So x plus 2x plus x is 4x. 2y plus y minus y is 2y. And negative z minus z plus 2z is 0, with 0 plus 4 plus 8 equaling 12. And now I have a new system of equations which has two variables and two unknowns. Sorry, not between those two, between these two. This is E1 plus E2 plus E3, and I used all of my equations between getting this equation and this one, so I'm good to, I can use these two equations from here on out to find my solution, and I will not have lost any information. Okay, so these two equations, I want to do the same thing I did before. I'm going to use my elimination technique to get rid of one of these x's or y's. I'm thinking that I want to get rid of the y, so I'm going to do this equation minus 2 times that equation. So I'm going to do, this is my new E2, this is my new E1. So I'm going to do E2 minus 2 times E1, and that'll give me another equation. So I have 2y minus 2y is 0. I have 4x minus 2 times negative x. Well, the negative signs cancel, so that's 4x plus 2x is 6x. And then I have 12 minus 2 times negative 4. Well, minus and negative is a positive, and 2 times 4 is 8, so 6x equals 8. So that means that x equals 4/3. And now I plug this into my previous equation. I can pick any of these equations I'd like that have just an x and a y, and that'll let me solve for y. I'm going to pick this one. So I get negative 4/3. That's x plus y equals negative 4. So that means that y equals negative 4 plus 4/3. This is 12/3. Or negative 12/3 plus 4/3 is the same as negative 8/3. This is my y value. And then I can plug both of these into any equation that has a z in it and get back my z value. I'm going to do this one. So we have 4/3 was equal to x plus 2 times negative 8/3 was y minus z equals 0. So z is equal to 4/3 minus 16/3. And so z is equal to negative 12/3, which is negative 4. So the point, which is the solution to all of this, is my x-coordinate, which is 4/3, comma my y-coordinate, which is negative 8/3, comma z, which is 4. And that is our solution. 4/3, negative 8/3, 4 is the point where all three of these planes intersect each other. Okay, so that is how we do one of these problems where we find solutions. Now, I want to go from here to one more technique to solve these, which is matrices. We're going to use matrices to solve systems of equations now. So what is a matrix? A matrix is a rectangular array. An array just means a collection of things where we have in every what we call entry of the rectangular array, have a number. And they're indexed like this. That's a 3. So this is called an M by N matrix. An M by N matrix looks like this, where we have, this is called the 1-1 entry, this is the 1-2 entry, the 1-3 entry, up to the 1n entry. There are n columns in our matrix, and this is the 1-1 entry, the 2-1 entry, the 3-1 entry, all the way down to the m1 entry, because there are m rows. Here's a row, here's another row, so on. This is the last row is the mth row, and then this here is called the mnth entry. So you have these rectangular sets of numbers that we can add and we can subtract and we can multiply and we can do other things. Determinants are probably the next thing that we'd talk about when talking about matrices. And we'll get to all of those things. But right now, I want to talk about how to use a matrix to solve a linear system. So let's say that we have a linear system. Let's say that we have x plus y minus z equals 0, and negative x plus 2y plus z is equal to, let's pick a number, 3, and let's say that we have 2x minus 3y plus z is equal to 7. Great, so we have this linear system, and we know how to use our combinations of these rows to find a solution to this linear system. But we want to try a new method. This method is going to be a matrix method, and it turns out that, like, if you look carefully at all the numbers that show up, this is the same as doing the elimination of the variables as we did before, but it's all a different way of looking at it. And matrices, this is a nice way to introduce matrices before we get into more complicated matrix stuff. So matrices have all kinds of applications. This is one of them, and this is maybe the first one that we can talk about to get a handle of what matrices are before we talk about other things that can be done with matrices. Anyway, I'm going to convert this system into a matrix, like so. I have 1, -1, 2. I'm just taking the coefficients off of my variables. And notice that I have x's, then y's, then z's, then constants in every equation. So this is the x column where I put x coefficients. And then I have 1, 2, -3. I have -1, 1, and 1. And I have 0, 3, and 7. Okay, so I have this matrix now. And what I'm going to do is something called row reduction. And I'm going to take this system of equalities and I'm going to row reduce it, and that row reduction will give me the solution where all three of these planes cross. So row reduction works this way. I want to get this matrix in a form where this is a 1, this is a 1, and this is a 1. This is called the diagonal of the matrix. It starts in the top left corner and goes down 1 and over 1 until I hit the bottom of the matrix. So sometimes the diagonal of the matrix will start in the top right corner and hit the bottom left corner. That happens when the matrix is square. This is not a square matrix because I have more columns than I have rows. I have 4 columns and 3 rows. If I had the same number of columns as rows, I would call it a square matrix, and then the diagonal would connect the top left corner with the bottom right corner. But this is not square, so it doesn't do that. So what I'm going to do is I'm going to take this top row and I'm going to add it to the second and third rows, multiplying as necessary, so that I can kill off all of the entries in the first column that aren't in the first row. So I want to make this and this 0. And the way I can do that is I can take this whole row and add or subtract it from this row and this row to get zeros in the first column. So if I add the first row to the second row, I'm going to get a 0 here because 1 minus 1 is 0. And then I add these together, so I'll get a 0 there, and I'll get a 3 here, and I'll get a 0 here, and I'll get a 3 here, because 1 plus 2 is 3, negative 1 plus 1 is 0, and 0 plus 3 is 3. So my top row remains unchanged as I do this. So the top row for my matrix is still 1, 1, negative 1, 0. But my next row becomes 0, 3, 0, 3. And now I'm going to do the same thing with the next row. If I take negative 2 times this row and add it to this row, I get negative 2 in the first slot, first entry, plus 2 makes 0, and that'll make a 0 in this corner where I want it to be. And then I get negative 3 minus 2 times 1 is negative 3 minus 2 is negative 5, 1, and then negative 2 times negative 1 is positive 2, so 1 plus 2 is 3, and then 7 plus negative 2 times 0, well, negative 2 times 0 is 0, 7 plus 0 is 7. So I do that, and let's recall that'll be 0 entry because 2 plus negative 2 times 1 is 0. So I get a 0 in my first entry. Then I have a negative 3 minus 2 times 1, which is going to be a negative 5. And then I have 1 minus 2 times negative 1, which is 3. And then I have 7 minus 2 times 0 is 7. So this is my new matrix that I received by row reducing. I'm not done row reducing, but I've done the first step in row reducing. I've gone from this matrix to this one here. And this one has zeros underneath the diagonal. So, as I said, this is the diagonal. 1, 3, 3 is my diagonal. And I want to have all zeros under the diagonal, all zeros above the diagonal, and ones on the diagonal. So now, from here, I continue. I'm going to divide the middle row by 3. So, the operations I'm allowed to do are I'm allowed to take one row and add or subtract multiples of it from the other rows. I am also allowed to take a row and multiply or divide all the entries in the row by the same number. So if I divide the middle row by 3, I get 0, 1, 0, 1. And now I'm going to take this row and add 5 times it to this row. So I get 0 times 5 plus 0 is 0. I get 1 times 5 minus 5 is 0. I get 0 times 5 plus 3 is 3. And 5 times 1 is 5. Plus 7 is 12. So to go from this matrix to this one, I divided the middle row by 3, and then I took this row, which is 0, 1, 0, 1, and I multiplied it by 5 and added it to the third row. I also want to get rid of this 1 above the diagonal. So I'm going to take this row here, 0, 1, 0, 1, and I'm going to subtract it from this row, 1, 1, negative 1, 0. So I get 1 minus 0 is 1. I have 1 minus 1 is 0. I have negative 1 minus 0 is negative 1. And I have 0 minus 1 is negative 1. Now from here I'm going to do the same thing that I did to the second row, but do it to the third row. I'm going to divide by 3 so that I get a 1 in the diagonal. 1, 1, 1. And then I'm going to have to take whatever I get there and use it to kill off that entry to make it a 0. So let's start that. We have 1, 0, 0, 0, 1, 0, 1, 1, 4, because I'm dividing by 3. And then I want to get rid of this negative 1. So 1 plus negative 1 is 0. So I'm going to just add this row to that row. And you might be wondering why I put a 1 here. I got a little ahead of myself, but one thing that you will, as you're row reducing, one thing that will happen is that since you have zeros under the diagonal, you can no longer take rows and add them to the first row and change the first entry. Or see, because there are zeros all the way down underneath this first entry in the diagonal, there's no way I can add these rows to rows above them and mess up that 1 being there. So there's no way that I can add a 0 to 1 and change the 1, or this 0 to 1 and change the 1. So I was getting a little ahead of myself, but these two will not change anymore because I have row reduced these two columns and have this is a 1, and this is a 1, and everything else is a 0. There's no way to change those 1s and 0s anymore by adding rows together. So anyway, I wanted to get rid of this 1, and I'm going to do that by adding this row to the first row. So I have, of course, 1 plus 0 is 1, 0 plus 0 is 0, negative 1 plus 1 is 0, which is what I want. I want to get rid of that. And then negative 1 plus 4 is 3. And now that I have this, the solution to my equation is given to me here in this column. So let me prove this to you. So I have, this says that since the 1 is in the x column, and I follow it across and I have a 3 here, that tells me that x is 3, this is the y column, and the 1 in the y column carries over to this 1 here, tells me that y is 1. This was a 1 in the z column, so z is equal to 4. And let's plug those into our original statement here and see if that works. So we have x plus y minus z is 0. And we claim that x is 3, y is 1, and z is 4. So is 3 plus 1 minus 4 0? Yes. So we satisfy the first equation. Let's look at the second. Negative x plus 2y plus z equals 3. So negative x is a negative 3, plus 2y is plus 2, and then plus z, which is 4, that's 3 plus, negative 3 plus 6 is 3. That works as well. So we satisfy the second equation. The third equation is 2x minus 3y plus z equals 7. So we have 2 times 3 minus 3 times 1 plus 4 equals, well, we claim 7, but let's count. 6 minus 3 is 3, plus 4 is 7. And that satisfies the last equation. So, from that, we maybe haven't proved that matrices solve the same problems that linear systems solve, and maybe we haven't proved that this will work all the time, but at least in this particular case, we feel confident that this matrix method got us the same answer as our, it got us an answer that satisfied these three equations. It got us what we were looking for, which is the solution to these three equations. And with that, we are now at the end of our episode for today. So next week, on Monday, we're going to talk about adding and maybe even multiplying matrices, probably taking determinants or whatever we get to in half an hour. And of course, send your questions to me. Email is mathjazz9@gmail.com. I have that on the screen now. So email your questions to me. I will answer them in the live stream. And have a great weekend. Take a break from learning some math this weekend, but be ready on Monday so that we can talk more about matrices and cool things that they can do. So have a great weekend. Bye.